This webcast continues in Worksheet 3E, where we are interpreting graphs that show accelerated motion. And so we're on the last problem, number 3. So remember, when we are given a graph, note what type of graph it is. This is a velocity versus time graph. And as I look at this, I see that the initial velocity is 0. That's not telling me anything about position. That says this thing is starting from rest, from a velocity of 0, and the velocity becomes more and more negative, so it is speeding up in the negative direction. Then from time 2 to time 4, it is moving at a constant velocity of -2 meters per second. Then the velocity starts moving back towards 0, so it is slowing down from in the negative direction until it reaches this point. And let me put that, it's always good to note the places on a velocity versus time graph where it crosses and changes sign. Here it's going from negative to positive. So at time 7, the velocity is 0 for an instant as it changes direction. After time 7, it starts speeding up in the positive direction, and then when it reaches time 10, it continues at a constant velocity of 2 meters per second for those last 2 seconds. So now that we've done that, let's give the time periods where this is moving in the negative direction. Negative direction is when velocity has a negative sign, and that's from time 0 to time 7 seconds. For that whole time period, the velocity has a negative sign. After that, from time 7 to 12 seconds, it's moving in the positive direction because the velocity has a positive sign, and it changes direction at time 7 seconds. Okay. Where is the object at rest, if only temporarily? Well, at time 0, right? It starts from rest, and at time 7 seconds. Both of those are places where the velocity is 0. Both of them, it may just be for an instant, right? But it's 0. Where is the object moving at a constant velocity? So we're looking for horizontal parts of this graph. And so that would be from time 2 to 4 seconds, when it's going in the negative direction at 2 meters per second, and from time 10 to 12 seconds, when it's going in the positive direction at 2 meters per second. Okay, then it says create an acceleration versus time graph. So to do this, I need to know the acceleration for each part of the trip. So for this, I'm going to make a little table here. For example, from 0 to 2 seconds. What's the acceleration there? Well, I see that the velocity is changing by -2, right? -2 meters per second, and it took 2 seconds, so it's at -1 meter per second, or meter per second squared. From time 2 to 4 seconds, the velocity is not changing, and so the acceleration is 0. From time 4 to 10, that period is, in that period, the velocity changes at a constant rate. I know that because it's linear. And so I can find the final minus initial velocity and divide by the elapsed time. And so that would be 2 minus -2, and the elapsed time is 1, 2, 3, 4, 5, 6. So that's 4 divided by 6 is 0.75 meters per second. And then finally, from 10 to 12 seconds, the acceleration is 0 again, because velocity is not changing. Okay. So for the first 2 seconds, the velocity, the acceleration is -1. And so I'm going to show that for the first 2 seconds, and then for 2 seconds the acceleration is 0 because the velocity is not changing. And I know for the last 2 seconds the velocity is 0, and then here from time 4 to time 10 it was 0.75 meters per second squared. Okay, so that would be our acceleration versus time graph. Okay, now it says find the average acceleration over the full 12 seconds. Well, average acceleration equals the change in the velocity divided by the elapsed time, and the change in velocity is the final velocity minus the initial velocity. And so I can go up to my velocity versus time graph and see that the final velocity was 2, the initial velocity was 0. So we have 2 minus 0, and this is meters per second, over 12 seconds. So that would be 0.167 meters per second squared. Then what's the total displacement over the full 12 seconds? Well, the displacement would be the area between the velocity versus time graph and the x-axis. So let me come up here. I'm going to show where the x-axis is. That's right here. And then I'm going to shade the areas. So here I've got a big trapezoid, and this is a trapezoid too, right? Or I could do it as a triangle and a square, so maybe I'll do it that way. Okay, so the areas for that big trapezoid in A, it's 1/2. I add the biggest base, which is 1, 2, 3, 4, 5, 6, 7, and the smaller base, which is 2, and multiply by the height, which is -2. And so that's -9. B is a triangle, half of the base times the height, and C is a square, which is just the base times the height. And so the delta x would be the sum of those. -9 plus 3 plus 4 is -2 meters. And what is the total path length that the object traveled? So the path length, remember, equals the sum of the absolute values of the displacements of each part of the trip. So I can use those same areas that we just found, but the displacement from time 0 to time 7, that was here, area A, the displacement was -9, but the path length is going to be the absolute value of that. So I'm using the same areas that I used to find the displacement, but I treat them all as positive areas. And so then I get 16 meters. Then it says, sketch a possible position versus time graph. For the motion of this object. So I'm just going to go back up here. Remember, we were moving in the negative direction and speeding up, then a constant velocity, and then slowing down, and then turning around to go to speed up in the positive direction. Okay, so let me do A first. So first I'm speeding up in the negative direction, then going at a constant velocity, and then slowing down in the negative direction. And so, so as I speed up, and then going in a constant velocity in the negative direction, and then slowing down in the negative direction. So that's like A. So here I'm speeding up. This is constant. And this is slowing down. Now it turns around. It moves in the positive direction and speeds up. And then it moves at a constant velocity. So this is speeding up. And this is constant. So that is the approximate shape of a position versus time graph. I don't know where it starts because the velocity versus time graph, that's a V, does not tell us the initial position. So I kind of assumed when I drew this that it started at a position of 0. If the starting position was different, this graph would move up or down. The vertical axis. So the shape of this position versus time graph would be the same. It's just where it is. So let me draw that in a little bit so we can see the whole thing. So the position versus time graph would have this type of shape, but it could move up or down the vertical axis depending on what the actual starting position was.